Hey everybody, in this video I'm going to explain the theory behind something called mass spectrometry, and in doing so we'll eventually teach you how to analyze and explain some simple mass spectra for elements and compounds. We'll begin with the theory behind mass spectrometry just briefly so you sort of know what's going on here and how chemists use this extremely valuable tool. The example we're going to use is shown here on the right hand side. What we've got in gray is a ramp, and at the top of the ramp are going to be three different balls that we can roll down the ramp. One's a ping pong ball, golf ball, and shot put. If you don't know, shot put is extremely heavy. Of course, we all know ping pong ball is extremely light, low mass, and golf ball somewhere in the middle. For this to make any sense at all and teach you how mass spectrometry works, there also needs to be something that applies a force to these balls as they roll down the ramp. And here we're going to imagine a hairdryer that is sort of blowing a cross breeze across this thing as they go. This very strange experiment is exactly what mass spectrometry does, and it's using something called deflection as a means to measure the mass of an object or of a particle eventually. You can imagine if there's a stream of air applying a force across this thing, if you roll something like the ping pong ball down the ramp, because the ping pong ball is very light, its mass is very low, it's going to get deflected a lot and maybe exit somewhere around lane 4 or 5 at the bottom of this thing. The golf ball is going to come down and be deflected maybe less and exit somewhere around lane 2. The shot put is going to come down and maybe barely be deflected at all because its mass is so high and exit somewhere around lane 0. This is beneficial to know because once you've done a bunch of these tests, you could then roll a different ball down this ramp, a ball maybe you have no idea what its mass is, and based on how much that one gets deflected, like let's say it's deflected to the same spot the golf ball is, you're going to know that this mystery ball has about the same mass as the golf ball. So this is a massive oversimplification of real mass spectrometry, but it is also essentially how it works. You can use deflection to measure mass. So how would each ball be deflected with the hairdryer on? We've kind of walked through that to give these two key ideas. If something has a heavier mass, it's deflected less. That's our shot put. If something has a lower mass, it's deflected more. That's our ping pong ball. Mass spectrometry does all of that same stuff. So now we're switching to the real version, just with atoms instead of balls rolling down a ramp. So here's a good model of how mass spectrometry works for atoms. I'm going to label the side by side of what you're seeing here with what we saw in the last example. The whole thing starts with a sample of atoms. In this case, we've got magnesium atoms. This is the same thing as the different types of balls that we were rolling down the ramp. Keep in mind, these atoms are a mixture of different isotopes. Since it's magnesium, we're going to see the isotopes 24 and 25 and 26. Conveniently, there's even 3 of them, just like there were 3 different masses of balls that we rolled down the hill in the last example. The first thing that's got to happen is you need to ionize those atoms. That means that you need to give them a positive charge for this to work. Once they are positively charged, you're going to accelerate them. This would be the equivalent of, the ramp. In the example before, it was gravity that was pulling them down the ramp. Here, we're probably going to use some type of a magnet or electric field. It doesn't really matter. The point is you're going to make them go really fast, and they're going to go through this tube. Usually the tubes are curved or looped in some way. But essentially, if you follow these dotted lines, those dotted lines are the balls, the equivalent of the balls rolling down the ramp here, traveling through this tube. As they travel through the tube, they're going to be deflected by some type of a field generator. So this would be the equivalent of the hairdryer that is deflecting them. It's pushing on them, just like the wind was pushing on the golf ball or the shot put. And what you're going to see happen is the exact same thing we saw happen before. Heavier mass particles are deflected less. So here, this line that I'm doing in blue, those are my heaviest particles, the Mg26, being deflected the least. Whereas lower mass particles, let's choose a different color, maybe green. Here, the Mg24s, this is like the ping pong ball, are going to be deflected a lot. You can even label each of the isotopes to match. So Mg24 is like the ping pong ball, Mg26 would be like the shot put. And then right in the middle are my Mg25s, which would be like the golf ball. When they get to the end of this tube, there's some kind of a detector plate that records where they are hitting on the detector, and there's a couple different things it can do there. But the point is, this information gets fed into a computer, and it spits out a graph that humans can then analyze to learn about the original mixture of atoms that went in there. And that graph has a name. It's called a spectra, or a mass spectra. Essentially, it's showing you a spectrum of the different masses of the different particles that went into the mass spectrometer. We're going to end this video by teaching you how to analyze a mass spectra. We'll start with a nice simple one. This is a mass spectra of a sample of the element boron. Let's break down what you're seeing here, starting with, what are these axes? What does this even mean? The horizontal axis, the bottom one, is what's called the mass to charge ratio. A little confusing because it's a ratio that bothers some people. If you're concerned about the fact that it's a mass to charge ratio, just know that almost all the time the charge is a +1. So what you're really looking at here is just the mass. You can imagine any mass, if you just divide it by a +1 charge, any number divided by 1 is still just that number. So you can think about this bottom axis as essentially just the different masses of the different particles that got pushed through your spectrometer. So that's how we can see the different masses. The vertical axis is the percent abundance, something you might have heard of before. That essentially is telling you how much of each of those different massed particles there were. Let's minimize that and get all this information out of the way and actually talk about the spectra you would see if you put a sample of boron atoms through one of these instruments. So first off, we have numbers on our bottom axis, 10 and 11. Remember, that is the mass to charge ratio. Since we already know the charges are almost always +1, we don't necessarily need to label that it's a +1, but I'll fill it in. Essentially, we're seeing the different masses that boron atoms can have. Here, there's just peaks. These blue lines are called peaks. Peaks at two different masses, 10 and 11. I just learned that boron comes in two different isotopes. Boron with a mass of 10 and boron with a mass of 11. That's essentially what we're seeing here, is the different masses boron atoms can have, and there's a name for those. They're isotopes. The other piece of information you get, besides the masses of the particles, based on how tall the peak is, you can go to the height of the peak and follow it over to the vertical axis. This one falls at 81.3. If you do that with the boron 11, it's a lot less. It falls at 18.7. You're also seeing how abundant each isotope is. The boron 10 is much taller. It means it's more abundant. The boron 11 is smaller, it's less abundant, and we've even got specific percentages here. It looks like 81.3% of these atoms had a mass of 10, while only 18.7% had a mass of 11. So this is how, mass spectrometers is one of the ways, the most common way that chemists get information about percent abundance of isotopes like this. So to summarize, here's what we know about boron from this spectra. Number one, there's two isotopes, boron 10, boron 11. Number two, we also know the percent abundance of each. And for a simple spectra like this, that's pretty much all you know, or you can tell from it. And the only other thing I'll add in is that you could do some extra work to calculate the average atomic mass for boron. I'm not going to walk through that, but right now we have all the information needed to do so, like that you could take that mass of 10 and multiply it by the relative abundance. Take the mass of 11, multiply it by its relative abundance, 0.187, get those answers, add it together, and calculate your average atomic mass for boron. So let's apply this to a new example. Here we've got a sample of magnesium being analyzed in a mass spectrometer. There's 3 questions, the same 3 things we just addressed for boron. Ideally, you should pause the video and try this yourself before watching me go over the answers. Assuming you've done that, or if you just want to follow along, here we go. Number 1 says, how many isotopes does magnesium have? Since there's 3 peaks, I know that there are 3 different isotopes. I can even be specific about what each one is. Mg with a mass of 24, Mg with a mass of 25, and Mg with a mass of 26. That's what my horizontal axis tells me. I can also find out which is the most abundant based on the heights of the peaks. Mg24 is the tallest. That is the most abundant isotope. I can even make a guess at what its actual percent abundance is. Maybe somewhere around 50, 60, 78% as my best estimation. 25 and 26, of course, a whole lot less. Maybe 25 is around 10%, and the 26 looks like a little bit higher, maybe 11 or 12. From this, you could approximate the average atomic mass of magnesium just by seeing that Mg24 is the most abundant. So that means its average mass is going to be, somewhere between 24 and 26. It's not going to be right in the middle at 25 because this 24 has a much heavier weight, right? There's a lot more of it. So you might expect the average to be approximately 24 point something. I don't know, maybe 24.5 or 0.3. So that's another example. Let's wrap up this video with a slightly more complex version of a mass spectrograph, this time for molecules. Molecules, if you don't know, are combinations of atoms. So, instead of just putting hydrogen atoms, single atoms through the instrument, you might put molecules where 2 hydrogen atoms are bonded together, and these 2 hydrogen atoms essentially make up one collective particle. And this is going to change some things. First off, mass spectroscopy, or doing mass spectroscopy, it's a really violent process. These particles get going really fast. They're colliding with each other. They're smashing into the walls of the tube that they're traveling down. And because it's such a violent process, these molecules, or when you put molecules through, they often can break apart into fragments. In the hydrogen molecule example, when you put these H2s, that's what this would be called, H2 molecules through the instrument, some of them might stay attached as H2, but you're also going to get some that literally break apart. So besides 2 hydrogens attached going through the machine, you're also going to have some singular hydrogen atoms going through the machine that have broken apart during this violent process. This means at the end of the tube, there's all kinds of different particles that are being analyzed. We're going to take a look at how it works for a sample of bromine molecules, which are Br2. So you can see right off the bat, there's not just a couple peaks here, there's lots of different peaks, and they're really spread out from each other. Let's start analyzing what we're seeing here. First and foremost, I like to give myself little models of exactly what the molecule is. In this case, luckily, it's a very simple molecule. It's just 2 bromines bonded together. So that's the first thing. The other thing you need to notice is that we're given some information, like bromine comes in 2 different isotopes. Some bromines have a mass of 79, others have a mass of 81. If you think about those 2 different possible isotopes and the fact that a bromine molecule is 2 bromines attached, you could imagine that some of these bromine molecules are made of 2 different bromine atoms, both of which have a mass of 79. So both of these atoms are the bromine 79 isotope, which means the total mass for that entire Br2 is the 79 plus the 79 added together. This whole particle has a mass of 158. You can then start to think about some of the other possibilities. Like, what about if some of these bromine molecules are made of a bromine 79 and others a bromine 81? That's going to have a mass of 160. And then, of course, that leads to the last possible combination where both bromines are 81, and that's going to lead to a mass of 162. And suddenly, if you are thinking about that, then you've got explanations for these 3 different peaks. Those are the 3 different ways that the bromine isotopes can be arranged in the bromine molecule. Some of the Br2s are this type. Let's use arrows to connect all these. That's the 158 peak we're seeing. Some of the Br2s are this type. That's the most common type with a mixture of each isotope. And some are the 8181 type, hence the mass of 162. There's also these much smaller peaks down here, straight at 79 and 81, and those can be explained by remembering that this is a violent process. So while I put in two bromines attached, some of them are going to be broken apart. So the 79 is just that, some individual bromine 79 atoms that were broken from the Br2 they were originally part of. Of course, the same thing for Br81. So that's about as complex as this video is going to go for mass spectroscopy. You can find, extremely complex examples, but this should be a pretty good introduction to get everyone started. That wraps it up. Thanks a lot for watching.